So I apologize for the cold, the temperature in the room. That we had a pipe burst yesterday, and they're still working on it, so it's a little bit chilly in here. Not sure where the time went, but the semester is almost over. So this is the penultimate of our seminars, Nano at Tech seminars. The final ultimate seminar will be in 2 weeks on December 11th, and the speaker will be Professor Chris Roy from BME. So it's a real pleasure to have Ali Adibi with us today. Ali got his bachelor's degree in electrical engineering from Shiraz University, then came to Georgia Tech for his master's in Double-E, and then did his PhD and a postdoc at Caltech before coming back to Atlanta as a faculty member in 2000, where he's currently professor and Joseph M. Pettit chair in electrical and computer engineering. He is editor-in-chief of the journal Nanophotonics. He's won a number of research awards, including a Presidential Early Career Award, a Packard Fellowship, and a career grant from the National Science Foundation, as well as several teaching awards from Georgia Tech. He's also a fellow of the OSA, the SPIE, and the AAAS. And so it's a pleasure to have Ali with us today.
Thank you, David, for the introduction. Good afternoon. Thank you for participating in this seminar. And I'm really thankful to the organizers for inviting me, for having the opportunity to talk to our campus people about some of our research in the area of hybrid nanophotonic materials and devices for integrated photonics. As always, I'm representing a big group of students and postdocs who did these works, and I just managed them doing this work. The field of silicon photonics is getting into a new realm these days because of lots of advantages of silicon listed here. Silicon is an abundant material, and it is available in platforms that are friendly for photonics. It's reconfigurable in the sense that its index of refraction and optical properties could be modified. There is a large IC fabrication backbone that supports photonics as well, and that's one of the main motivations that silicon got into the field of photonics. It can be integrated with electronics on the same chip, and dense integration because of the confinement of light. Lots of applications. Interconnection is a big deal these days. It has been a big deal for, a long time. Information processing, the field of RF photonics, millimeter wave photonics, analyzing wireless signals in the optical domain because of the large bandwidth of optics. Sensing, there are a number of companies that came out of Georgia Tech research in doing such sensing. And then, these days, the end of Moore's law and the new paradigms for computing has brought back the concept of optical computing. And whenever you have a chip, you try to offer a solution. And of course, LiDAR, which is very important for autonomous cars, among others. There has been a lot of advances in silicon photonics in the last 2 decades that we are really, riding on those achievements, ability to talk to non-optical signal like RF signals, millimeter wave signal through high-speed modulators. The faster they are, the faster we can put the data in optics, and therefore the faster would be the processing. Integration of sources and detectors. Silicon is not a direct semiconductor, so we cannot make lasers and detectors at some wavelengths in silicon. So when we make them in other materials, we need to somehow seamlessly bond them, and that has happened. Reduction of loss has been a major driver in this technology. And then, of course, when you have good waveguides and resonators, we can form a variety of functional devices that then they add up together to form a complete system on a chip. And then, there are adjacent technologies like photonic crystal technologies, where they try to somehow fill in the gaps of device technology that conventional devices cannot achieve. What we do is primarily resonance-based integrated photonics. This is an example of a photonic resonator, which is a microdisk. The radius could be somewhere between 1.5 micron to 100 micron, but miniaturization will push us to use a smaller and a smaller. This is a waveguide that brings light into the system, and if the wavelength matches the resonator's wavelength, and then if the coupling is proper, the signal goes into the resonator. As you see, the dip in the transmission corresponds to the mode of the resonator. We have a lot of modes. And then when we zoom in one of these lines, we get the bandwidth, and then from there we define the quality factor, which is a measure of the sharpness of these resonances. We have achieved quality factor of 3 million for this, and then it's just coming up. Of course, a resonator like this has some problems. We have a lot of high-order modes. The distance between adjacent modes of the same nature, free spectral range called, is very small. And then, in order to critically couple it to the resonator, we always have a little bit of issue because the waveguide has to be very close, since the large resonators confine a lot of their energy inside and don't talk to a waveguide outside very well. So in order to solve these problems, we developed this miniaturized technology here. This is a same microdisk resonator, but reduced in size all the way to 1.4 micron. By reducing the size, we have the fundamental mode as shown here, still confined, but then the higher order modes get leaky and then they get out. And then if we punch a hole, quote unquote, or etch a hole inside the resonator, we affect the high order modes, kick them out, because as you can see, the fundamental mode is mostly in the periphery of the resonator. So this way, and by optimizing the fabrication process thanks to our IEN facilities, we were able to show the first devices at 1.5 micron with quality factors of 100,000. And now you can see that over 70 nanometer, I only have just one mode. Just to emphasize, I'd like to compare this with what I showed a few seconds ago. This is a big resonator, and this is a small resonator. So now the ability of having only one mode in a large bandwidth allows me to do a lot of clever things. Now, one idea is to have a so-called add-drop structure, where a variety of wavelengths enter the structure, and then the resonator selects one of those and then send it into another waveguide, separate wavelengths in a wavelength division multiplexing system. Now, the real thing is that if I mix some of these resonators, then I will be able to somehow shape this spectral response, because each resonator is responsible only for a tiny bandwidth and doesn't talk to the rest of the frequencies. So this is the idea that if I have, let's say, 6 resonators here, you will see that the drop strength is now at 6 wavelengths, each corresponding to one of the resonators. And then for each one of the resonators, I can develop architectures like coupled structures in order to shape this resonance and have it a little more flat band or Chebyshev type and so on. So now little by little, I can shape a spectral response using these resonators, each taking care of the business in a small bandwidth. And natural thinking of that would be a spectrometer, where I have an array of these resonators, and in order to save a space, we just wrap the waveguide around them, as shown over here. And these resonators each has a little different wavelength decided by the size, and then they cover a wide bandwidth range. Each one selects one wavelength and sends it out of the structure. Using this, we can have a 90-channel spectrometer in a very small area, and we can have down to 0.1 nanometer wavelength resolution, 60 nanometer bandwidth, and less than half a dB insertion loss. I mean, this is just for a simple chip that can be manufactured and doesn't need sophisticated detector cooling and, you know, large size gratings and so on. That's a very, very small miniaturized tool for spectroscopy. Now, this is the actual device we fabricated. So the key thing here is we have an array of waveguides that when the light is selected by the resonator, it just couples it to that waveguide, and the waveguide brings it out. So the resonators are half here and half there. And I kind of interleave them in order for the adjacent channel not to be close. So 1, 2, 3, 4, 5. And then I can repeat these structures in 2 dimensions if I wish. And then at the end of each waveguide, I have a scatterer that just sends the light out. And then I will put a camera on top in order to monitor what happened in the structure. The measuring system is here. What I do is I bring a tunable laser and then tune the wavelength and expect that by tuning the wavelength, light should just switch between resonators back and forth as the wavelength changes. It goes to each one of the resonators, and that's what you see. So it clearly works in that range. Now, there's a little bit of, you know, apparent crosstalk that's just because of the saturation of the detector, not the exact, you know, crosstalk issue. So one of the advantages of silicon over some of the other material is the ability to reconfigure it. You can use the name tuning, modulation, somehow changing its properties by an electronic or another optical signal. And there are different means that we can use. The first one is by injecting carriers into silicon, electrons and holes. We change the index of refraction. In the second approach, thermo-optic effect, we just heat it up, and then that changes the index of refraction. In the third approach, we kind of make a slot in it and then fill it up with polymers. And in the fourth, we use optomechanical tuning, which is more along the lines of optical MEMS, when you can have 2 structures that one of them is kind of moving, and by applying a signal, you can bring it down or up and change the effective resonance, index of refraction. These are the properties of any tuning mechanism. It's not surprising to expect very fast operation at very low power, very low loss. So everything should be, you know, pushing the limits in order to make these devices practical. This is the example that we did for making a reconfigurable filter by changing the index of refraction of silicon. So in this structure, we have a unit cell that's order 1 or order 2 filter, and then we just repeat that. And then by repeating it the same way you multiply polynomials, you just increase the degree of the filter, which is identified by the number of poles in the transfer function, and of course the number of zeros. So that's the technology we developed for DARPA, and that's the actual micrograph of that. We have 4 resonators. This is a kind of a order 2, so that's order 4. And then a filter like that can be modified by applying electric signal to these heaters that we put on the structure. And that filter can be a notch filter with tunability, or the same filter by a series of different control signals can turn into a bandpass filter with controllable center wavelength and controllable bandwidth. So you can have one structure, and by applying electronic signal, you can get different functionalities out of that with, you know, speeds that are for the heaters in the ballpark of 100 nanosecond time. So if silicon is so good, the question is, why do we look for other materials or hybrid materials? Well, part of the problems is that silicon cannot handle high powers. And that's always a problem. At high power, silicon nonlinearity kicks in. If your signal is analog, it's dead. The same way nonlinearity in transistors are bad, the same way nonlinearity in photonic devices is bad. The quality factor, even though we got a few millions, but when you're pushing the limit to tens of millions, you will stop, because silicon has 2 photon absorption and free carrier absorption. Also, there's a problem that occurs in all integrated photonics, not silicon. This is an example of microdisk resonators and a heater in the center of it when there is no electromagnetic field. When you design it up to any significant digit that you want in nanometer size. But when you fabricate it, it's not going to be that size. There's a little bit of fabrication imperfection. That changes the resonance wavelength. Now, for publishing a paper, you don't care, because you have a tunable laser, and then you tune it to that wavelength, and then you report what you want. But if you want an array of these, each one of them modulating a frequency or wavelength for a WDM, then you do care. So you always have to trim your structures, and that has to be low power. This is not, as I said, this is not just silicon, it's any material. And this a technique has to be developed for that to be low power and fast. And then, you know, if we use thermal, of course, like this, then the speed is going to be low. Now, when you start kicking out the power, as here is shown, originally, you have a very nice resonance, the blue curve. But when power goes up, the heat generation and the free carrier loss start to compete. And then at some point, you will see that your resonance has a biastable behavior. That's just the problem of high power in silicon that cannot handle. So let's try to solve one problem at a time. The goal eventually is to have a hybrid material platform that has different layers. In this example, silicon nitride, at points of it, graphene and metallic structure and so on. The idea is I have a substrate. At different locations, I want different devices that may require different functionalities that silicon cannot have it. You want to have a nonlinear device. Silicon nonlinearity might be very small. You have a better nonlinear material. You want to have a very high quality factor. Silicon nitride, as we will see in this talk, is very good material. But you just want it there. And then silicon has some properties that surpass everybody else's. So you want a combination of these in a hybrid material where different locations can have different properties. So the first thing that we did was, oops. That's not my fault. Okay, it's here. That's okay. All right. All right. So this is what we call it a double-layer silicon that we developed. The concept is simple. We have 2 silicon on insulator, silicon on oxide wafers. I grow very thin layer of oxide, about 10 nanometer to 30 nanometer, depending on application on each. And then I bond them together. Now, although I said in probably 30 seconds, it took us about a year to optimize this platform to get quality results. But then this is what we get. This is a waveguide. Silicon, and the middle oxide is probably visible, even from distance. And then the resonator. Now, using this material, we were able to demonstrate resonators with quality factors that are in the ballpark of the single-layer silicon. That means the quality of the material is not sacrificed, both small resonators and large resonators. A comparison of this work with other works, the quality factor with size. Our case was bonding. There's deposition, bonding, deposition, and deposition. And you can just compare the numbers to see the quality is really improved. This is the transverse electric mode, and this is transverse magnetic mode. Some have most of their energy in the middle region, and the other one have the TM and TE. TM has most of the energy in the oxide between, and then TE has most of the energy in silicon. So this is an excellent platform for modulation tuning when you want silicon property to kick in. This is an excellent material if you want to etch oxide and replace it with a material to sense, for example, where most of the energy is there. We use TE. Now, the reason we started this is because now I can think about this as a capacitor, as shown over here. Silicon, silicon, and oxide. And by applying a voltage, I can accumulate carriers there without requiring a current. In contrast to conventional ways of using a PN junction and push the carriers in or take the carrier out by a current, I just apply a voltage and capacitively I accumulate the carriers. Now, I apply a voltage as shown here, and clearly I can get a shift. So that's the structure. One electrode is shown, is placed at the center of the silicon. The other one is placed at the periphery. Now, the advantage of this structure is multifold. Number one, I can clearly see that by not requiring a PN junction and a current, I can reduce power consumption. Two, I will have a trade-off between the capacitance, which tells me that what voltage can be applied. So I want some charge. Large capacitance allow me to work with very low voltages, and a small capacitance allows me to work with large voltages. Large capacitance has a larger RC, lower speed. Small capacitance has a smaller RC, higher speed. So there is a trade-off that I can play with using this structure. And most importantly, if there is any problem in the size of the resonator and its resonance wavelengths, all I need to do is to apply a DC voltage, to put some DC carriers in, and then fix that problem without keeping a current in all the time or keeping heat in all the time. So that allows me to reduce the power consumption of the device. This is the, the design structure as shown over here. Adding the contacts is always a challenge because you have to add them in a place when electromagnetic field is minimum. And then this is the, the RC structure that you can see. There are some resistances in the structure. And depending on the resistances and the capacitances that are involved, you will get an RC time constant which defines your speed of operation. The polarity of the voltage, of course, makes a difference. If your charge is provided by holes and electrons, like in this case, P and N, then you're going to get more index variation because only mobile carriers, electrons and holes, change your index. If in this case, you're also relying on acceptors and donors to some degree, then you're not going to get that much phase shift or index shift. And you can see that for good polarity, you get a larger resonance shift because that, all the charges come from electrons and holes. A complete system for characterization, which was done in Georgia Electronic Design Center, GEDC, Professor Rolf's Center for high-speed characterization. Aside from all these elements here, what you do is you control your polarization, you send the light into the waveguide, you monitor the light out. Now, these are the systems that allow you to monitor its frequency response, its bit error rate, so on and so forth. But at the end of the day, you just send the light into the waveguide from a fiber, out of the waveguide from a fiber. This is the response, the frequency response, and you can see that you will easily get 3 dB bandwidths we believe it's going to be more than 15 gigahertz. It's limited by the characterization tool. The eye diagram is shown over here for 15 gigabit per second. And these are, two zoomed eye diagrams. This is the performance of our modulator. About 30 gigabit per second 55 femtojoule per bit. That's the energy you spend to convert 1 bit from 0 to 1. 10 dB total modulation depth and insertion loss of 5 dB. By tweaking and re-optimizing, easily a factor 2 in both speed and power consumption can be achieved. This technique solves a couple of problems, the trimming need and power consumption. But they don't address the high performance at high powers and low quality factors, meaning a few million. Those are inherent properties, so we need another material. And silicon nitride has 20 times less effective nonlinearity. It doesn't have free carrier absorption. It's technically an insulator. So we could get, in principle, ultra-high Q resonators. This is some examples of the fabricated devices, silicon nitride on a silicon wafer. You can see that we have got Qs of 16 millions. And now by adding chemical mechanical polishing or CMP to our system through the new addition to IEN, we're expecting to easily get above 30 million, which is a state of the art. So that's like an order of magnitude better than silicon. We developed a very sophisticated optimized silicon nitride process. Again, it took us probably about a year to optimize it. And now with that, we are able to get quality factors, that we feel it would be reaching to, more than 30 millions. This is the example sidewalls. And the material on the top is the flowable oxide, which can be removed. That's just like a mask, which will be removed at the end. But very good qualities have been achieved. That's for the resonator that I showed, quality factor of 10 million for 60 micron. And this is without any CMP. And without CMP, this is among the best results published to date. With CMP, it should get to, as I said, about 30 millions. Now, if silicon nitride is so good, why don't we use silicon nitride only? The problem is that we cannot reconfigure or tune silicon nitride easily. It's a dielectric, so I cannot inject carriers. Carriers out of question. Its thermo-optic effect is weak, so I have to apply a lot of heat to change it. So now we have a material like silicon that can be modified more easily. We have a very low loss material, silicon nitride. So now the marriage of the two should give us a much better material platform. And that's what we did. So here is a silicon on insulator wafer again. Here is an oxide on silicon. And then we grow silicon nitride here at IEN using LPCVD technique to have a high quality silicon nitride. And then we put oxide on the top, we bond the two, and then we remove the substrate and the oxide, and we get silicon on nitride. Now these trenches are important. They are placed far from each other, like 500 micron from each other, which in integrated photonic language is a lot, because your device is tens of microns. So now we put it there just because there are air bubbles that will develop at the bonding time if we don't put that. So you can easily see that when trenches are there, there is no air bubbles. When there is no trenches, there is air bubble. And again, this took us about a year to optimize to the quality that is competitive and not sacrificing either silicon or silicon nitride property after bonding. This is the fabrication process. So we first fabricate our devices in silicon, which are smaller because of the higher index. And then we come back and fabricate devices in nitride. So the key advantage of our technique is that the material development is done all prior to any fabrication process. Because like the position of nitride is always at high temperature, it will affect silicon. So this way, we just develop the material using this technique first, and then we will fabricate our devices. And now this is an example of coupling light from silicon using a grating, and then there is a silicon waveguide that we taper it down. This is the zoomed version of the taper down to 15 nanometer. When you make your structure very small, you expand the field, it automatically goes into the nitride waveguide underneath. So not much alignment is really necessary, I mean reasonable. And then it goes into a nitride waveguide. We couple it into a resonator in the nitride. That's the reason we wanted nitride to begin with. It gives us very high quality factors. And then the output signal will come into silicon through another taper, and then by a grating, it will come out. So this shows the response, and it's very interesting to see that over a wide bandwidth of more than 50 nanometer, we don't get much loss because of going between one layer to the other and coming back. Our assessment, experimental, is that we get better than 97% efficiency going down and up between the two layers. And then you can see that resonators in nitride still get very good quality factors. Now, using this material, we developed a new modulator architecture that uses an existing technique called coupling modulator. Let me compare the two philosophies. In conventional modulators, like the one that I showed before with double-layer silicon, we have a waveguide and we have a resonator. We apply carriers either by p-n junctions or by a capacitor to the silicon resonator. That changes index of refraction, that changes the resonance wavelength. So if the light from waveguide is coupled to the resonator at its correct resonance wavelength, I get 0 output. If I shift the resonance of the resonator, it doesn't couple to the waveguide. So the waveguide light will go out unaffected, bit 1. This way I do the digital modulation. Now this is very effective, and I can use a very high Q resonator, which is a very sharp resonance. So if I tweak it a little bit, well, I go from 0 to 1. I don't need to apply much power. But the problem here is that when I am switching between resonance and non-resonance, the resonator doesn't respond immediately. There is some light inside the resonator that needs to scatter out. And the higher the Q, the longer this time is. So the way I like to bring our minds closer is to think of it as a dam. And this is a water channel. And I want to send some water from this dam to this channel that has much smaller capacity than the dam itself. Like a high Q resonator has tens of thousands of times more photons than the one that waveguide wants. So now, in this example, what I do is that I will just empty the dam and fill the dam up when I want to get any change in this channel. This simply means that it takes time to fill it up and then give some into the resonator and then empty it up. That's why even the highest quality factor resonators are coupled to the waveguides so that their effective quality factor is like 10,000. Because you need to reduce your Q in order to get the bandwidth that you want. This bandwidth power trade-off is one of the problems. But what I do in here is that we say that, OK, what if I can change the coupling of the two? Just for the sake of argument, bring the waveguide closer or farther from the resonator. Now, this simply means that I will bring the wall of the dam down a little bit, just enough to get the water into the channel and then bring it back up. This is going to be much faster than this case, because here I'm not changing the resonance wavelength of the resonator. It's always at the same resonance. It always keeps a strong electromagnetic field. It just tweaks a little bit. So this will be much faster because I don't need to empty it up, and then it keeps the quality factor intact. So that's somehow a means of breaking that idea. This shows some simulation results as a function of the coupling coefficient, coupling strength of the two. Of course, the stronger the coupling, that means I can get faster signal into the resonator, into the waveguide. So when the quality factor of the resonator is large, I need to tweak the coupling coefficient much smaller to go from 100% to 0%. When the quality factor is smaller, of course, I need to change it a lot. So now, the idea is that how do I move that waveguide? It's fabricated. Well, we don't. What we do is we form a resonator in the nitride layer, and then it is coupled into two waveguides in the silicon layer, which is technically one waveguide that goes through a round trip and come back. Now, I modify the phase of that waveguide by applying the p-n junction in this example. So the waveguide is in silicon, the resonator is in nitride. Now, this way, I'm effectively changing the coupling because I do two-place couplings, and by modifying the phase between them, I can make them constructive or destructive. So this way, I need only a small amount of shift in here in order to get complete bits, ones, and zeros. The reason I do it in silicon nitride is because I can get a very high quality factor in the nitride resonator than the silicon-only resonator. This is an example that you can see. If I go between 1 and 2 different couplings, you will go from a low transmission into a high transmission. This is the actual view graph of the structure, silicon nitride resonator and silicon. And then the coupling between them is done by the tapers, as I mentioned before. This is a tapered signal in silicon that allows the signal to go into the nitride waveguide, and then resonator, and then come back up. To test it, for a quick and dirty test, we fabricated the device, and we use heat to change the, the phase of silicon. By shifting the temperature by about 5 degrees, you will see that you go from almost 0, minus 20 dB, all the way to a very large transmission. So that's what happens when you change the temperature. Of course, this is not done by thermal because thermal is slow. This is done by applying a voltage to a p-n junction as shown over here. So all the modulation is done in silicon, and here I'm modulating only a waveguide, not a resonator. So it's not limited by the lifetime of the resonator. And then I have my resonator at a fixed wavelength there. This is the response of my p-n junction that actually shows the diode response. This is the performance of the system. This is the transfer function as a function of frequency. The transmitted signal divided by the incident signal as a function of frequency. And you can see that the 3 dB bandwidth for this example was 12.5 gigahertz. For this resonator, if I wanted to use the resonator only, the conventional technique, I would be limited to 1 gigahertz because of that filling and emptying the structure. Insertion loss is 3 to 5 dB. Some other numbers, bit error rate of 9 times 10 to the minus 4 will allow me to have 10 gigabit per second. This is just the first try. It can easily get into 30, 40 gigahertz operation. The next step is now to start with the silicon nitride, but then adopt the double-layer silicon technology, the first technology that I mentioned, to reduce the power consumption, avoid having p-n junctions. So that requires a 3-layer material, silicon, double-layer silicon, silicon, and then silicon nitride. So this is the chart for the bonding process, where first we do the double-layer silicon as before, and then we grow nitride, and then we bond them together, and we get this 3-layer material. Some examples of the devices fabricated, again, silicon, and nitride. Coupling is done using tapered couplers. Signal goes into this structure, And that is, again, the response, very good tapered coupling. And the quality factors are also in the million range, 1.2 million for this example. So it's not an easy material to develop, but thanks to extensive development and IEN facilities, we were able to get into this place. Now, this is a recent result, unpublished yet. So that's what we are working on now to demonstrate a material in this platform. I guess there is just one thought in here that we have looked into it. And one idea is if we can etch silicon oxide in this platform and fill it up with polymers, electro-optic polymer, then I can have a slot resonator or a slot structure, and then have a very power efficient, high speed system, because electro-optic effect is very fast, and electro-optic modulators in slots with 100 gigabit per second have been demonstrated. These are at the infancy yet, so we have to develop the process for them. In the remaining time, I want to shift the gear and talk about another material that is very important beyond silicon and silicon nitride, and that's silicon carbide. Now, a lot of things have been listed in here, and I'm not going to go through all of them. Those who are interested in implantable devices know that it's biologically safe. So one idea is for making brain probes and so on. Silicon carbide does the job. And that's something that we are looking into with a colleague of mine at Carnegie Mellon University. It has very good second and third order nonlinearities. And then by making carbon vacancies in it, you can make quantum dots. Now, it's also very good material at visible, same as silicon nitride, of course, less developed, but with a difference. Silicon nitride is an insulator, silicon carbide is a semiconductor. So you can still inject carriers and get faster modulation and tuning performance out of it. So there are lots of things. The reason we got into this is primarily the nonlinear and quantum aspects that silicon carbide can bring. Potentially can generate single photon sources, single photon detectors. And that's the area that we are collaborating with a couple of colleagues in Italy on that, who are expert in silicon carbide material. So what did we do? If you look at the silicon carbide, it's usually grown on top of silicon, but you cannot make devices in it because index of refraction of silicon carbide is lower than silicon. It's about 2.1, 2.2. Silicon is 3.3. So light will go all into silicon. So you have to remove silicon somehow, and people undercut or do some other things. When we started this research, the quality factor of resonators in carbide was very low. Part of the reason is that the stress at the silicon carbide will result in low quality of the film in here and a lot of scattering, so you get a lot of loss. So what we did was we used our bonding technology. We put oxide on top of a dummy silicon wafer. We put oxide, and then we bonded this material upside down, and then we removed the silicon. So now when I remove the silicon, the culprit, the bottom layer, will just come on the top. And I can do whatever I want with it. Definitely polishing. So then we did chemical mechanical polishing to the surface to make the quality better. A very simple idea that used our knowledge of bonding in order to bring the quality factor to the record high, as I'll show in here. So this is the original sample. The top surface of it when we get it is reasonably good. That's the AFM results. And RMS variation is about 1.4 angstrom because they polish the top surface. The problem is the bottom surface. This is when I bond it and bring the bottom surface up and monitor it with AFM. You can see that. And this is after chemical mechanical polishing. Of course, we did not do aggressively this. If we do that, at least we should get 1.4 angstroms. But that by itself shows that our simple technique can reduce the scattering from that by a factor 3. We also developed an electron beam lithography and etching process to fabricate the structures. Okay. The material is not perfect. You see these voids in here. But even through that, we were able to fabricate resonators in it. So these are an array of figures that I try to explain. These are a couple of different resonators with different sizes and different resonances. The key figure here is this one that shows our observation of quality factor as a function of the radius. Now, for this, we achieved quality factor of 142,000, which was 3 times the existing world record. Now, the unpublished results, this is published, but the unpublished result that we have got by making this structure better is now in the 250,000 regime. So just by a simple thing, we're bringing a material that was thought to be too lossy into a regime that now we can get structures out of it. We can get photonic performance out of it because quality factor is getting into the ballparks of the numbers that are attractive. I just flush out a couple of slides that show other materials that we are working on. This is double-layer graphene on silicon nitride, graphene. This is similar to silicon nitride, silicon. The reason we use graphene is because, on paper at least, graphene should have very low resistance. Now, the speed is limited by R, resistance, and C, capacitance of this device. By reducing the resistance, we should get 100 gigabit per second on paper. Now, we are still working on this because of the sheath resistance of graphene is higher than what expected, but that's another material platform that we have developed, being able to transfer graphene by wet transfer technique, put oxide in between, and then combine it with silicon nitride technology. These are some other hybrid material platforms. This is 2D materials, molybdenum sulfide, molybdenum selenide. These are metal dichalcogenide, which combine a transition metal like molybdenum with a chalcogen like sulfur and selenium. And they have active properties. They are direct semiconductors, 1 atomic or molecular layer thin. And we are working in making quantum dots out of those. The paper just came in ACS Photonics, where we are, ACS Nano, where we are showing lateral heterostructure in it. I mentioned silicon carbide. This is our polymer work, where we have a silicon waveguide, etch a slot in it. It's proven that your mode can be completely or mostly confined in the slot, and then putting an electro-optic polymer and changing that electro-optic polymer through electro-optic effect will allow to develop very fast modulators. And that's the double-layer silicon on nitride. And let me conclude that silicon photonics has gone this far with a lot of success. I mean, there's investment from US government and industry to make foundries to mass manufacture silicon photonic chips. AIM Photonics is an example of such investments, and Europe is investing. So I would expect soon we will see people sending their tape out to these foundries instead of fabricating it themselves. But all this capability can be augmented by combining silicon with materials that brings properties that silicon does not have. And then that's the vision of this work, and then the results that I showed, either in double-layer silicon or silicon-silicon nitride, suggest that for sophisticated systems that push the limits of speed and power consumption and size and density would eventually require some kind of marriage between different materials. They could be silicon, silicon nitride, 3-5 semiconductors, silicon carbide, polymers, or other materials. And that's the approach that hopefully can push silicon photonics into higher applications and hopefully into consumer and non-consumer markets. Thank you very much for your attention. Well, the question was explain a little bit more on the metric Q over V. Well, when you look at a resonator, let me, and by the way, I apologize for not mentioning the funding people, but these are the sources of funding for us. So if I go to one of these slides, well, the key thing is that quality factor by itself shows how you can confine your mode inside the structure and therefore build up energy inside that. But then the question is that, is your energy built up over hundreds of microns or over tiny nanometers? The key thing at the end of the day is energy density, which is, number of photons per unit volume. Now, two properties have two different aspects of this story. Quality factor is about the confinement of energy, putting it more and more in the resonator. And then mode volume, which is in essence the volume that your mode occupies, normalized by the index of refraction. Let's forget about that. So now mode volume is technically the volume where your mode is concentrated, not just the resonator, because the mode is mostly around 1 micron of this, and then 100 nanometer up and down of that structure. The smaller the mode volume is, the better the structure is. The larger the Q is, the better the structure is. The ratio Q over V, V is volume, yes, yes. And there are cases that, for example, in plasmonics, you have resonators that have quality factors of 100 compared to 10 million. But then they're competitive because they confine your energy at the surface in a very small mode volume. And at the end of the day, that's the parameter that defines one structure over the other.
Okay, let's thank Ali one more time.
Thank you.